Okay, I promised you guys a little thermodynamics practice problem for today. And so let's work this one together. Let's take a look at it. So the problem says, calculate the heat in joules required to warm 50 grams of ice at -5 degrees Celsius up to steam at 105 degrees Celsius. And we know that heat in joules is equal to mass times specific heat capacity times the change in temperature. So at a first glance, this might look like a simple problem until you think about it. Well, what is my heat capacity? What's my specific heat capacity? You know the heat capacity of water, right? We know that piece. C for water is 4.184 joules per gram degree Celsius. But this problem is not just about water. This is about starting with ice, warming it up to its melting point, so from -5 up to 0 degrees where it would melt, and then the energy input required to melt the ice, and then to heat the ice up to its boiling point, and then the energy required to boil it to become steam, and then to heat that steam an additional 5 degrees. So this is actually a pretty complicated problem, and let's sketch it out. We quickly did one that had one phase change, but this is a little bit more involved than the example that we did in class. And the example that we did in class was a long, long time ago. So let's warm our brains up and start thinking about chemistry again. All right, so we don't have to draw the phase diagram to solve this, but I think it's going to help you make sense of it. So if we think about our water sample, our 50 grams of ice, plotting the temperature here and the energy input here, we can think about it this way. So we're starting out below 0 degrees. So we're starting out down here, and we're going to require, for our ice to get up to the melting point, we're going to require one bit of energy input right there. And the energy would be increasing as the temperature increases up to that phase transition. And at the phase transition, so at the melting point, which would be B here, we're still putting energy in, but all of that energy is going to changing the phase of our water from solid ice into liquid water. And so we keep adding energy, but all we're doing is changing the phase. Now this is not at all to scale, so don't judge me harshly for that. I'm just squeezing in a little diagram for you for clarity. So once it's all melted, right here, it'll all be liquid water. So from C, for all of this little leg that I've labeled C, we've got liquid water that's being warmed from 0 degrees up to its boiling point at 100 degrees. And at the boiling point, we have another phase change. So at the boiling point, we'll have to put energy in, additional energy in, but the temperature won't change. It'll hold steady at 100 degrees. And then, let me see if I can squeeze that in there. So segment E would be after all of the water has been heated into steam and all of it's been boiled, it's all converted from liquid to gas, then segment E would be heating it from its boiling point an additional 5 degrees to get it up to 105 degrees. All right, so we're going to have 5 different energy pieces here and then add those together. So our Q total is really the sum of all of those little Q's, all of those little energy pieces, and we need to figure out what those are. And so in order to do that, let's write down what we know. So if we're starting with 50 grams of ice, so that first piece would be MC delta T for our ice, where mass is 50.0 grams. The heat capacity of ice is not the same as the heat capacity of water. The heat capacity of ice is 2.04 joules per gram degree Celsius. That means that it takes an energy input of 2.04 joules to raise the temperature of 1 gram of ice by 1 degree Celsius. So it's lower than that of liquid water. Our delta T, so what's our temperature change here? We're starting at -5, so our T initial, remember delta T is T final minus T initial. we're going to heat it up to 0, up to the melting point. So TF minus TI would be 0 minus negative 5. So that's a 5 degrees temperature change. So that's the first piece. This is for segment A. This would take this amount of energy right here, 50 times 2.04 times 5, would, let's see, what would happen to our units? Our degrees Celsius would cancel out, our grams would cancel out, and we would have an amount of joules that corresponds to warming our ice up to the melting point. Well, for our phase changes, it's not Q equals MC delta T. It's we have a heat of fusion, a delta H. So we have a delta H of fusion, which is freezing, and another delta H for our vaporization, which is boiling. That's how much energy is required to make those phase transitions. Let me slide this over a little bit. So the delta H of fusion of water at 0 degrees or ice at 0 degrees, the same thing, people. Joules per gram. And then for boiling, it takes a lot more energy input, 2,260 joules per gram to convert it from liquid water into steam. Why is that number so high? What's going on there? So what has to be overcome to make the phase transition from liquid to gas? And I know you all just said out loud to me through the computer, I know you all just said it would be the hydrogen bonds. We have to break all those hydrogen bonds. Remember, every water molecule is polar. And if we visualize the electron cloud around that water molecule, we've got lone pairs of electrons with that give the oxygen atom a partial negative charge, and then our electron deficient hydrogen atoms that have a partial positive charge. And water molecules are very strongly attracted to other water molecules through this attraction between the electronegative, electron-rich oxygen on one water molecule to the electron-poor, partial positive hydrogen atom of another water molecule. And so water molecules always hold on to other water molecules. And then to boil that, we have to break those hydrogen bonds. And so that's why this little side note here, but that's why the enthalpy of vaporization is so high. All right, so far we've got our energy for segment A. So for segment B, how much energy is it going to take us to take our ice at 0 degrees and without changing the temperature, convert it all into water at 0 degrees? Well, it's going to take this much energy, 333 joules per gram. So 333 joules per gram multiplied by how many grams of ice we have. And we have 50 grams. And so that's segment B. We add that amount of energy, it'll all be converted to water at 0 degrees. To warm that water from 0 degrees up to its boiling point, up to its vaporization point, would be the energy for segment C, and that would be Q equals MC delta T. So MC delta T for our water would be 50 grams again. Now the C we're going to use is the specific heat capacity of water, 4.184 joules per gram degree Celsius. And the temperature change, my final is 100, my initial is 0, so that is a 100 degrees Celsius temperature change. And that's segment C. And we'll add in segments D and E. So for D, it's going to take 2,260 joules per gram to vaporize my water, to convert it from liquid at 100 degrees to gas at 100 degrees. And so I'll multiply that by the grams that I have, 50.0 grams. Then I'd have joules per gram multiplied by grams, grams cancels out. So that piece is segment D. And then the last little bit of energy I need to input is to take my gas, my steam that's at 100 degrees, and heat it 5 more degrees to get it to 105 degrees Celsius. So that will be a Q equals MC delta T, but for steam. And so my mass is still 50 grams, sorry. The specific heat capacity for steam is almost the same as ice, 2.03 joules per gram degree Celsius. And my temperature change is going from 100 to 105. And so that is a 5 degrees Celsius temperature change. All of that would be my segment E. And so the total amount of heat required, the total joules required to take ice at 50 grams of ice at -5 degrees, heat it all the way up to melting and then all the way up to boiling, all the way into hot steam at 105 degrees. It's going to be the sum of all of these little pieces of energy. So this piece heats my ice from -5 to 0. This piece of energy is my phase change from ice at 0 degrees to liquid water at 0 degrees. This amount of energy is the energy required to warm water at 0 degrees up to water at 100 degrees. And then this is the vaporization energy. And then this last piece is the energy required to raise the temperature of the steam. So let's calculate that. You probably already did it while I was talking. 2.04. So 510 joules here.